AC voltage applied to a capacitor. Let us apply an alternating voltage E equals to E naught sine omega t to a pure capacitor of a capacitance C. The capacitor will get changed first in one direction and then in the opposite direction. If Q is the charge on plates at any instant, then Q equals to CE. But E equals to E naught sine omega t. Q equals to C E naught sine omega t. From the definition of current, I equals to dQ by dt. I equals to dQ by dt equals to d of Ce naught sine omega t by dt. Therefore, I equals to Ce naught omega cos omega t. I equals to E naught by 1 by C omega cos omega t. Therefore, I equals to E naught by 1 by C omega sine omega t plus pi by 2. Maximum current will flow when sine of omega t plus pi by 2 is unity. That is, I naught equals to E naught by 1 by C omega equals to E naught by xc. Therefore, I equals to I naught sine of omega t plus pi by 2. Capacitive reactance xc. The peak current through a capacitor I naught equals to E naught by 1 by C omega. If we compare it with the peak current through a pure resistor I naught equals to E naught by R, we find that 1 by C omega is the effective AC resistance of a capacitor, which is called capacitive reactance, denoted by Xc. Xc equals to 1 by omega C equals to 1 by C of 2 pi f. Therefore, f is frequency applied. Definition. Capacitive reactance is defined as the opposition offered by a capacitor when current flows through it. The units and dimensions of capacitive reactance are same as that of the resistance. In terms of Xc, the RMS EMF E equals to Ixc. Phase difference. Instantaneous EMF E equals to E naught sine omega t. Instantaneous current I equals to I naught sine of omega t plus pi by 2. The phase of EMF equals to omega t and phase of current equals to omega t plus pi by 2. Therefore, the phase difference between the current and EMF is pi by 2 radians or 90 degrees. The current through the capacitor is ahead of the EMF applied across it by pi by 2 radian or 90 degrees, or EMF is behind current by 90 degrees. Phasor diagram, vector diagram, Argand diagram. Power in a purely capacitive circuit. Instantaneous power equals to EI equals to E naught sine omega t I naught sine of omega t plus pi by 2 equals to E naught I naught sine omega t cos omega t equals to E naught I naught by 2 sine omega t cos omega t equals to E naught I naught by 2 sine 2 omega t. Average power over a complete cycle The average speed equals to integration from 0 to t of E naught I naught by 2 sine 2 omega t dt by integration from 0 to t dt. The average speed equals to E naught I naught 2t integration from 0 to t of sine 2 omega t dt. The average speed equals to 0. It is already defined, therefore integration from 0 to t of sine 2 omega t dt equals to 0. Therefore, no power is consumed over one cycle. After capacitive reactance, Xc directly proportional to 1 by F for dc is to F equals to 0. Therefore, Xc equals to infinity. That is, a capacitor offers infinite opposition to the flow of dc through it. In other words, a capacitor blocks dc. The two plates of a capacitor have a perfect insulator between them in the form of a dielectric. When the two plates of a capacitor are connected to a source of dc supply, such as a battery, then momentarily the two plates will be charged with the potentials of the terminals of the battery. Thereafter, no current will ever flow in the circuit.